Good afternoon and welcome back to early modern Europe. I'm going to do something a little bit different today in that I've got a story to tell you. A story about this, the vexing question of retrograde motion. And you're thinking, I don't understand that sentence at all, but you will. And the story I have to tell you today is about this thing that we call the scientific revolution. And one of the things that we have to start with, this basic understanding of the world that we live in, is that we are all children of the scientific revolution. We live in a world in which, contrary to some people at this particular moment in time, we believe and understand, even more importantly, science, scientific inquiry, scientific experimentation, scientific theory. We know that our universe makes sense from a scientific and mathematical point of view, that we can understand this world that we live in if we pay attention to those things. Now, obviously, I'm a humanities professor. I teach history and religion. And yet, I also live in the modern world, and I recognize the functional and central role of science in the world that we live in and the way we look at the world. We are children of the scientific revolution. We look at the world and say, we can figure this out if we ask the right questions, if we test things in the right way, if we do this methodically, we can understand. It's not unknown to us. And it's the interesting thing about the story that I'm going to tell, that we now, situated in the universe as we understand it, which is infinite and complex and big, right? That the larger the universe has gotten, the more understandable it has become. Back in the earliest days, the world was a small place. The universe was a small place. And even though it was so small, it was baffling, mysterious. It felt arbitrary. People didn't know how it worked, why it worked, what made it work. They weren't even sure of what it was made up of. And that's even beyond the more philosophical and religious questions of, where do we come from? How did this all get started? This is a story about us looking at the world in which we live and trying to figure out how it works, what makes sense and what doesn't. And how do we get to a point where we know a little bit more than we did the day before? That's what this is about. And so the story I want to tell you today is trying to figure out this question of retrograde motion. And no, I'm not going to tell you exactly what that is yet. Because what I want you to do is I want you to see what the ancient Greeks, at least, thought of the world that they lived in. This universe that we inhabit. And it's this, right? This is the way that some Greeks thought of the world, the universe as we lived in it, right? Now, if you think about it, this makes perfect sense, right? Because if you're just using our basic sense experience and our sensory input, this is what the world looks like, generally speaking. The Earth Because from our perspective, if you just look out your window or you're driving along, the earth looks, right, flat. It's not, and people are going to realize that pretty soon, right? So any of those, honestly, anybody who believes that the earth is flat right now, they're just trolling. They don't actually believe it. Even if they say to them, oh yeah, absolutely. No, they're just trolling. They're modern trolls. That's all they are. That's just it. But back then, right, if you're just looking, that's what it looks like. And then you'll notice, right, the ocean, the primeval ocean, the ocean of heaven, which is farther above. And then beyond that, right, there's the firmament with the stars. That's that dome in the sky. Well, because when we look out at the world, minus all the clutter, it looks like a dome, doesn't it? That's what it looks like. That's how we perceive it. That's the limit of our vision. But the limit of our vision isn't the limit of creation. It's not the limit of existence. It's just what we can see. And that's a really good way for us to think about it. This is a really good place for us to start, because this is just showing us the limitations of what we can physically see. And that's the start. That's the basis. This is a concrete way of looking at the universe from the most simplified version, right? The night sky, the lights in the day, they all look very small from our point of view. Like you can put your thumb in front of the moon or the sun and blot it out. Well, it can't be that big then, right? And you say, well, why do they say that the ocean of heaven is above, like the primeval ocean? Well, from our perspective, in the spectrum of color that we can see, the daytime sky is blue. You know what else is blue? Water. And at night, right, it's a dark blue, almost black. Well, so is the water at night, isn't it? And so they assume that if the sky and the sea look the same, they must be made of the same stuff. And that's what's beyond. And beyond that, they don't know. The pillars of the earth and the underworld, again, these things make sense. Where do you bury people? Underground or in caverns? At least the Greeks did. Not every group around the world buries the same way. Some burn the bodies, some bury the bodies, some have burials at sea. Some have sky burials, where all of the elements of the human body are taken back up by birds and other things. How we bury people, how we deal with the dead, it's just a part of life. And the Greeks, well, that's where they put their dead. And so that must be where the underworld is. That's where people go afterwards. The pillars of the earth, right? That just explains the rock, the foundations of the earth. From a purely simplistic view of the physical universe, this one makes sense. It does. Except it doesn't. It doesn't make sense. There's a problem. There's a big problem, especially for the observant. The ones who look up at the nighttime sky, and they don't just look at the wonder of it all. They start looking at the bits and pieces, the specific things. They start looking at each of those little lights and know that they are something unique, right? And so they start looking at them. And they start making observations. This is how they're going to figure out sailing early on, even at night, which you can do. It's not that complicated. But you have to figure out what's going on above your head. And so they look. I mean, they've already noticed that the moon goes through phases, that the sun seems higher and lower on the horizon, depending on the season. And they start to develop these things into mythological stories. And they're great, they're awesome, right? The difference of seasons and all the rest, and they have lovely explanations, etiologies in which they explain the origins of these things. But there are these people, they keep looking, and they run into a question. And this first question is, there's a problem with the firmament with the stars. Ancient people believed that it was just a fixed dome, right? That maybe turned around, right? Like we're on the inside of a snow globe, but it's the outside of the globe that rotates, right? And then somebody turns it during the day, and at night you get a whole new group of stuff, right? So there's this dome, this firmament. It's fixed. That's what firmament means. Firmament with the stars. And so it's just this kind of thing that kind of glides around us, right? We stay put. The universe, or at least that fixed dome, it's a sphere maybe even, it moves around us. Except there are things that didn't work that way. The Greek essentially is translated as wanderers. The wanderers in the nighttime sky baffled them, completely, utterly baffled. Because what the wanderers didn't make sense. Because you see, what they did is that if everything moved in one direction, that's what they thought, the wanderers went backwards. Retrograde motion. That's all it means. Backwards. They went in ways that seemed particularly unnatural. And so they called these nighttime firmament pieces wanderers. Do you know what we call them? Planets. That's what a planet means. Planet means wanderer. Planets wander in ways that don't make sense to the ancient Greeks and to others around the world who watched the nighttime sky very carefully, very specifically. It didn't make any sense. How can things go backwards in the nighttime sky? That's the question. There it is. That's the way it works. Now, interestingly enough, the ancient Greeks are going to start wondering about all of this. Now, the first one that we need to look at is Anaximander. He was living from 610 to 546. I'll put that down here. 610 to 546 BCE. And I see that my writing went up underneath my slide, so I'll have to write that a little bit lower. 610, 546 BCE. Anaximander is important. Now notice something. He's expanding the model of the universe out a little bit. It still doesn't make any scientific sense, but you can see he's pushing and probing. He's trying to figure out how these things might work, right? There's the Earth, which he kind of configured as a cylinder, right? He's incorporating some of around, but also that we still live on a flat surface. Don't ask me how this is supposed to work mechanically, right? If you're a physicist, don't come at me with, that doesn't work at all. I know it doesn't work at all. Just let's go with that. But you can see what he's trying to do, right? Where does the light come from? Well, there's this solid sphere out there, and beyond that is this rim of fire. Right? Again, he's trying to figure this out with the limited tools that he's got available to him. And so the stars are actually just holes in that sphere. The larger the hole, the brighter the star. So that's awesome, right? So that's why the sun is so much bigger. And that maybe in the space between the Earth and that sphere, maybe that's where the wanderers are. But he wasn't sure. He really had no idea. But what was really important about Anaximander is that he's going to be the one who introduces a mechanistic view, meaning a mechanical and physical explanation for why the world and the universe works the way that it does. He wants to move beyond the mythology and the supernatural explanations for the universe. And so there he is, a long time ago, saying, you know what? I don't think it's the sun god pulling a chariot across the dome of the sky. There's got to be a better explanation. And so he starts to develop a theory. And the interesting thing about theories, of course, scientific theories, is that they're true until you prove them wrong, which is why we're always tinkering, we're always expanding, we're always exploring, we're always improving, right? It's right until you prove it wrong. Well, what we're going to see is that a lot of people are going to say, that's not right, that's not right, and they're going to show the evidence for it. And that's the key to all of this, right? We learn over time through experimentation. It's the fundamental concept of science. And we have to show our work. And we have to show our evidence. And, as we all know, somebody else has to be able to replicate that experiment using the same variables. If they can, right? But then you keep pushing forward. It's like the whole business with masks during this pandemic. We have learned over time, because that's the way that science works, through experimentation, what works better, and why it works, right? We didn't all know that in February because we didn't need to, because nobody had really done that same amount of difficult, scrutinized testing with lots of variables and lots of experimentation and then coming up. And then we put up a theory and we say, okay, that's what we know going forward. And then until somebody proves that one wrong. And then we move forward. That's how science works. It's amazing. And that's what they're doing here, right? I mean, we look back at this and go, oh, come on, that's not. But it's better than saying that it was the sun god pulling a chariot across the dome of the sky. Yeah? And Anaximander is essentially saying, those are great stories, but they don't tell us how it happens. Right? And he's the first one to push the boundaries to say, it's got to make more sense than that. And that's all about us using the brains that we have to figure things out. And it takes curiosity, it takes humility, it takes patience, and it takes a dedication to asking big questions and little ones. And so they're going to continue to do this, right? They're going to continue to ask these questions and explore these things. And we're going to get people who are going to continue to probe and to push, like Pythagoras, right? Pythagoras, who lives from 580 to 500 BCE. He postulates something that we now take for granted. Well, except for those yahoos who are trolling all of us. He postulates a spherical Earth, right? A sphere, all the way back then. And so, again, if you read any yahoo, it's a flat Earth. Pythagoras, long time ago, and not the only one, because frankly, do you know how we know that the Earth isn't flat? Go out on the open ocean. You don't even need geometry, right? Although that wouldn't be a bad idea. Go out on the open ocean or an open lake. And I think I've talked about this before, but this just bears repeating because, golly, the very fact that we have to even mention this is just one of those things that blows my mind. It gives me headaches. As a historian, it just drives me straight round the bend, right? So if the Earth is flat, which it's not, right? Honestly, 21st century, and we still have to say this out loud. If the Earth is flat and you have two boats, right? And they're coming at each other. If the Earth is flat, they're going to see each other, the whole ship. One's going to be just really small, right? The one far away from you, it's going to get bigger and bigger. You're going to see the whole thing, though, if the world is flat. It's not. Just not the way it works. The Earth is curved. And here's a real thing. If you know that part of the Earth is curved, you can extrapolate out that the rest of the curve is going to be that. I know. It's fascinating, isn't it? Honestly. All right. If the Earth is curved, which it is, two ships coming toward each other, what are you going to see first? The tops of the ship, right? That's what you're going to see first. That's the way this works. Pythagoras figures a spherical Earth because he's been out in the open ocean. Even the Mediterranean's good enough. Oh, look. But that's taking basic, fundamental human observational skills and extrapolating out into a better understanding of the world around them. That all of a sudden, this notion that the world is flat is just ridiculous, and people have thought it's been ridiculous for a very long time. Very long time. Pythagoras is also going to realize that the morning star, Phosphoros, and the evening star, Hesperos, were in fact the same object, Venus. And he realized that he starts to come up with a notion of this thing that we call a cosmos. Which means a well-ordered, harmonious universe. The universe that we live in makes sense. And it follows certain rules, certain principles. It makes sense. And if we don't understand it, that's our limitation, not the cosmos being a mystery, right? It simply is saying to us that we've got something to figure out. We've got a question that we need to answer. It's an engineering problem. How does it work? Right? And if we don't know, then we have to build ourselves up and we have to think about those steps that are going to allow us to understand how it works. Now, I will say this, right? Pythagoras was very much of the opinion that he would put a lot of importance on the power of aesthetics, the aesthetics of geometry and mathematics, rather than experimentation, right? And so he abstracted it in a sense. But let's be clear that he found something truly beautiful in a structured, harmonious way of the use of geometry and mathematics. And that's true. And what we're going to realize is that those abstract concepts can actually and do describe and help us to explore everything that we want to explore. Pythagoras is going to see in all of the universe shapes, these geometrical solids, especially the sphere. And in them, he's going to see the ratio of the world. And in those things, and in our exploration, and in our examination, in our articulation, especially through mathematics and geometry, we can understand anything. Now, Pythagoras was a bit more of a romantic, as it were, when it comes to the beauty of mathematics. He wasn't as pragmatic, and obviously he wasn't as focused on experimentation, but that, boy, it makes a difference. Because now you're starting to introduce into the common language of the scholars and of people that these things matter and that they can mean something to how we look at the world and how we engage in the world. Now, the next best person on this little travel through time, and in our story about this vexing question of retrograde motion, is somebody who's going to essentially overwhelm the story for a very long time. And that's a nice young chap named Aristotle. Aristotle lived 384 to 322 BCE. And he's going to, as he does with everything, explore and categorize everything that he observes. So many of our scientific fields are fields of study and discipline in the academic realm and just in the world come from Aristotle and his categorization. He is going to observe and he's going to put things into categories. Well, one of the things he does is that he observes the world around us, the universe. And he's going to say, aha, I've got it all figured out. Essentially, he's going to propose that the heavens, right, everything above us, are literally composed of 55 concentric crystalline spheres to which celestial objects were attached and which rotated at different velocities. That's the universe, right? In Aristotle's physics, bodies moved to their natural places. Stones fell because the natural place of heavy bodies was at their center of the universe. And that was why the earth was there. And that there's a difference, essentially, between the earth, which is corruption, and the heavens, all the way up to the sphere of the prime mover, which is perfection. And so he orders the universe in these 55 concentric spheres and explains everything in that way. And you're thinking, that's goofy as all get out. yes, but in his context, it seemed to make sense. And because he was right about so many other things in that time period, and for a very long time, his categories are going to stick, right? Aristotle was the great scholar of the ancient Greek world, and it's going to have a huge impact on the entire Mediterranean and up into Europe for a very, very long time. Aristotelian thought is going to be the thing that essentially trumps everything else. And his view of the universe, that's going to stick. Right? There's the Earth at the center of everything. The moon, Mercury, Venus, sun. And so, but you're saying, well, wait a minute. That doesn't really explain retrograde motion. No, not really. Because even if they're all, right, rotating at different velocities, that doesn't mean they go backwards in the nighttime sky. I mean, if you squint and look funny, I suppose, right? But Aristotle didn't spend a lot of time on this. And that was his best explanation, and it seemed to essentially mollify folks, except it really didn't. There are people who are going to say, whoa, wait, excuse me. And that's where we get our next Greek thinker. And this is some of the best stuff, right? Because there's a guy who's going to live not long after Aristotle. His name is Aristarchus. And Aristarchus is going to get it right. This guy gets it right. Aristarchus, 310 to 230 BCE. I just want you to take a look at that, right? Just look. You're seeing something? You're saying, wait a minute. That's the way it works. You mean to tell me that Aristarchus in 310 to 230 BCE got it right about 1800 years before Nicholas Copernicus? Yep. You think, why did it take so long then? Well, first, his original writings on this were lost in the destruction of the Great Library of Alexandria in the 5th century of the Common Era. When the Library at Alexandria burned, that was lost. That, and if you think about it, people at the time were like, well, it doesn't make any sense. Doesn't make any sense. Because what he posited was that the Earth rotates and then goes and then orbits the sun. Like it does. But if you think about it, people at the time were like, Aristarchus, you're goofy in the head. That doesn't make any sense. If we are spinning on an axis, and that's how we get daytime and nighttime, right? Which we still name wrong. We say sunrise and sunset. The sun does no such thing. The Earth spins until we can't see the sun and spins again until we can, right? Rotates on its axis. The sun does not rise, right? Just one of those things to think about. You want to talk about moonrise and moonset? It's a better, you're in safer territory there, because that at least, spins around us, rotates around us, orbits, not the sun. And yet we still say sunrise and sunset. Sunrise is at 7:59 a.m. in the dead of winter. No, it's not. That's when we rotate around again. I'm belaboring the point, but I hope you get what I mean. Anyway, so he's saying, okay, the Earth rotates on an axis and we all orbit around the sun. And they're like, oh, if that's true, why can't I feel the speed? Because that would be amazing, right? Why can't I feel the Earth spinning or moving through space? Hey, Aristarchus, how come? Why is it, Aristarchus, that when I jump up in the air, if the Earth is spinning, why don't I land way over there? Or the Earth spins under my feet and all of a sudden I'm 50 feet in a different place. If I jump straight up, how come that doesn't happen? Why am I not perpetually having motion sickness? Because we're moving so fast through space? What are you talking about? See how that could confuse a lot of people? I mean, because if you think about it, right, you can't feel the Earth rotating, and we're rotating really fast. How long does it take for the Earth to turn around once on its axis, spin on its axis once? 24 hours, right? Well, the Earth is a big place. About 24,000 miles around circumference, give or take, which means it's spinning at about 1,000 miles an hour. That seems pretty fast. And it takes us 365 days to orbit the sun. That's a nice chunk of distance. Why don't we feel that? That's what people are asking Aristarchus. Because from their limited point of view, from their limited sense experience, that doesn't make any sense. How could that possibly be true? Which is another thing we're going to have to add to all of this to explain how this can even be possible. That's where that nice young fella named Isaac Newton comes in. He's got an explanation for that. But you see, now the other thing is that this view contradicts the prevailing view of motion espoused by Aristotle. Right? The other thing, and this is for the more scientifically inclined, the final key objection to this model is the failure of other observers to detect what is called stellar parallax. Right? Under his model, the closer stars, right, should show a periodic shift in position to and fro against more distant stars over the course of the year as the Earth orbited the sun. Interestingly enough, parallax wasn't actually viewed, not detected, until 1838 using very careful telescopic observations. He had figured out stellar parallax 2,000 years before anybody even saw it. He was right. But he was going against the common wisdom, right? The accepted tradition. He was going against Aristotle, for heaven's sakes. Who is he? He's not Aristotle. And so this is one of those occasions where it doesn't even mean, you don't need religion to be the bad guy in the whole scientific thing. You just have to be somebody who is offering up some observation and some modeling that is different than the conventional wisdom. Everybody knows that Aristotle was right, and they're going to go with that for a long time. It ain't the Bible they're worried about, it's Aristotle. Contradicting Aristotle, Aristarchus was right, or much closer to being right. And yet, he was on the wrong side of this conversation because his modeling was different than the great scientist, the great scholar, Aristotle. And then, of course, the materials were lost. And now we have essentially kind of bank shot references to them from other documents from that period of time that mentioned what Aristarchus was talking about. We don't have his actual piece. And so it disappeared. And because he was really challenging conventional wisdom, people didn't want to listen. Think about it. Oh, he had the explanation, give or take, and we turned our backs on it. Not because of religion, right? Which is always seen as the standard, bugbear in all of this, but because it just went against accepted tradition. And so they're going to move forward past this, and they're going to say, "Oh no, let's try somebody else." And so, a few hundred years later, we're going to get a guy named Ptolemy. (120 to 180) in the Common Era, and he is going to reaffirm the Aristotelian model. Yep, that universe, and you've seen those images, right? Earth is at the center, and then you get all the lovely concentric circles and the beautiful art and all that kind of stuff. The problem is how he explained the problem of retrograde motion. I mean, Aristarchus explained it. I mean, it makes perfect sense with some tinkering that we're going to see yet, right? Because that really depends on our point of view. You could see how it could work, that it looked like things go backwards, right? Ptolemy is going to say, "Oh no, I've got it all sorted out." And he posits this. He posits that there is a point in space called an equant, E-Q-U-A-N-T, equant. It is something he just kind of conjured up out of his own thinking. And what it does is what it shows here on the little illustration here. It's not the best, but it's the best one I could find. The equant is that point inside that red circle. Those are planets, the wanderers. And there's this point around which this kind of imaginary point in space around which the planet orbits, right? And so the planet orbits around the equant as it goes around the Earth, right? And that's why things look like they go backwards. And you're thinking, he's just making stuff up. Really, he is. But that, again, was pushing against trying to figure out a flaw in Aristotle's system. And so what he was actually doing was not so much solving the problem as he was solving the problem of the problem of Aristotle, right? Oh, no, Aristotle's not wrong. He just needed a little bit more observation, and I figured it out. And so that preserves Aristotle's model of the universe. Done. He was more concerned about preserving Aristotle than he was about figuring out what actually was happening. And you can see that happen throughout the course of history, where we're so concerned about maintaining the status quo that we will bend over backwards, even if it goes against science, to maintain the status quo, to maintain the equilibrium that we have. We don't want things to change, and so therefore we're going to say, oh no, it's this way, it's fine. It's the people who run around and say, oh, no. The pandemic isn't really a problem, right? It doesn't really exist. It's no worse than the flu. What they're afraid of is change. They're afraid of having to do things differently and having to think about others than themselves. And so what they're doing is that they're twisting the situation to preserve the status quo, to keep everything the way it is, so that I don't have to do anything differently, even though what that different thing is just wearing a mask or doing social distancing or washing your hands. I mean, really, on the cosmic level, right, and the historical level thing, this isn't that hard at all. But that's how far people will go to preserve tradition, the status quo, conventional wisdom. They'll work so hard that they'll actually break the system. The equant, think about that. This nonsense, made-up point around which planets orbit just to preserve the notion that the Earth is at the center of the universe and thus Aristotle's system. I mean, because if you think about it, the interesting thing about all of this is that we're working so hard to preserve the notion that we're at the center of the universe. Because that's what we perceive. Everything revolves around us, and we're just egotistical enough to believe it. When it doesn't take anything away from our uniqueness to admit that we live in a big universe and that it doesn't revolve around us. We don't lose anything by that, but it changes. It deviates from the status quo, and boy, that makes people nervous. And yet there are still people pushing. Let's explore. Let's continue on. And so we get that. We get people like that who are going to say, maybe we should think differently. And we jump ahead rather a long way. Ibn al-Haytham, Arabic scholar, 965 to 1039 in the Common Era. He wasn't an astronomer per se, but he was a scientist working in one of the great laboratories of civilization in all of the Middle Ages, and that is the Muslim Middle East. They were sprinting ahead of everybody else because they were using all of the old Greeks' materials, mathematics, physics, all the other sciences, and then they just kept sprinting forward with it. And Ibn al-Haytham, one of the great scholars of all of human history, was most well known for his methodology in investigation. In particular, he used experimentation to verify theories. And you're thinking, wait a minute, that's just called the scientific method. Yes, yes, it is. Or at least it shows those similarities. He wanted to push, but he knew that in order to push, he needed to use experiments. Now, the biggest difference is that he did not fully articulate the notion that all experimentation, you need to make sure that you do the same variables and you'll get the same outcomes, right? That's a little bit later. We're going to get to that in just a moment. But he pushes this out there, that the only way to really understand something is to base that off of experimentation. His were not as precise, a little bit more random, but the idea was still there. And of course, the root of the word experiment is experience. That's all science is. We have an experience, we write down those things, and then we see if they can be replicated. And by that, you test theories. That's the only way to do it. That what was really important about Ibn al-Haytham was that he moved it out of the purely theoretical into the practical. Okay, that's a great theory. How do we make it work? How do we visualize that? How do we make it happen so that we can see it, so that we can experience it? And he said, if learning the truth is the scientist's goal, then he must make himself the enemy of all that he reads. If learning the truth is the scientist's goal, then he must make himself the enemy of all he reads. And what he meant by that is that that's awesome, let's prove it. Let's find the evidence, let's make that. And if it's not, let's figure out where it went wrong. Don't just read something and accept it blindly. Challenge it, push it. Experiment with it. The idea is simple. The idea is particularly clear. Push, poke, prod, question. And he did this as a devout Muslim because he knew that every experiment that he ran, everything that he discovered said more about the universe that Allah had made. And to him and to all the Muslim scholars, that was awesome. The more you learned about the universe, the more you understood how great its creator was. Now, whether you're religious or not, you can see that's a pretty motivating factor to learn more and more about the world. And make no mistake, that idea was pretty consistent in Islam, Judaism, and yes, Christianity. What always became problematic in any place were the traditionalists, the keepers of the status quo. Didn't matter the ideology or the religion. It's the people who are in charge who are most allergic to change. They're the ones who fear it. And so whoever is in charge, whoever is in positions of power, they are going to use the tools at their disposal to blunt change, to stop innovation, or at least to slow it down, or co-opt it. He's out there trying to figure things out. How to push, how to explore, how to experience, how to prove theory, or at least to verify it. The only way to figure that out is by doing. And so he kept pushing, and that's why he's important. Because other scholars are going to take note of this methodological system of experimentation that he's pushing forward. It's not just happenstance. It's not just all these kinds of random things. You've got to be systematic about it. You've got to be methodical about it. Step by step. And don't take anything for granted. And don't lock yourself into what others have said just because they said it. Verify it. Push on it. If it's not quite accurate, then keep going. If you can prove it, awesome, right? Then you've done your job. But you got to keep going. And so they do. The scholars keep chugging right along, right? One of my favorites, a monk, Christian, right? Guy named Roger Bacon, 1214 to 1294 in the Common Era. And let me bring up his image. There he is. Right? That's Roger Bacon. He asked a really important question. How does one make knowledge trustworthy? Right? Essentially, how do you verify? How do you know what you know? And how can you, where's the evidence for it? How do you make knowledge trustworthy? I mean, I think we're asking that question right now, right? When we watch the news, how do we know what we're getting is true? And so he articulated some of the stumbling blocks, right? People had believed that if something was logical, it must be true. And every philosopher is going to explain to you that in formal logic, not everything that is logical is true, right? It may make logical sense, but that doesn't mean that it makes real sense. And so he says there's some stumbling blocks. One is reliance on faulty authority. And I think we're seeing that today, right? Some were wrong because they had relied on a supposed expert who was wrong. And so, right now, and yes, this is just the way this works, the person who is heading up the president's task force on the coronavirus is a radiologist. Well, that's a problem. We need an epidemiologist, not a radiologist. And so he is giving faulty information. But because people see that he's an authority, they figured that because he's an authority on a thing, he must be an authority on other things. And because he's an authority about medical things, he must be an authority about all medical things. And that's not right. But people will rely on that authority for their truth. And because he gets it wrong, they all get it wrong. Roger Bacon also says there's another stumbling block. It's called reliance on popular opinion. Some people are wrong because they relied on popular opinions or belief that were wrong. I know you'll find this hard to believe, but sometimes a widely held belief doesn't make it true. Like this QAnon conspiracy, right? No, those things aren't true at all, period. Just because a lot of people believe them doesn't mean that it's true. That's a faulty way of thinking, right? It's my favorite thing. No, the world is not flat. No matter how many people on the internet with clever YouTube channels say that it is. It isn't. Stop it. Or how about this one? Bacon talks about a reliance on personal bias or vanity. Others were wrong because they just wanted things to agree with, their pet ideas, and to conceal their ignorance through pride. Okay? Well, I'm right because I'm right. That's what I want to believe. That's not the way truth works. That's not the function. That's not how it works. Right? And concealing your ignorance through pride. right? Does that sound at all resonant with what's going on today? Finally, Roger Bacon's going to argue that sometimes there's a reliance on a rational argument. He calls the most dangerous because some people are wrong because they believed in a logical argument, that things were presented logically, and therefore they must be true. And we know that that's not always the case. You can make a logical argument and be wrong. It makes sense, but it's not right. And so Roger Bacon is going to get us to start thinking about, how do we know what we know? And others are going to be asking those questions. But it's, how do we make that knowledge trustworthy? He's going to poke and prod at how we know what we know and how we come to trust what we know. And that's going to take experimentation. And Roger Bacon is another one that's going to really push forward this notion that the best way to find out is to examine it, to run experiments diligently over and over and over and over again. And that if you're going to figure it out, somebody else is going to have to be able to run your same experiments and get the same results. If not, you did something wrong, or it didn't work, and you'd better figure out why. Roger Bacon pushes us, just like Ibn al-Haytham, about the world around us. And these are important steps. These are huge steps. Without these steps, we don't get to people like Galileo and Isaac Newton. We just don't. But that does bring us now into the early modern period. And you're thinking, whoa, phew, man, you're an hour in, Dr. Grant. Thank goodness you're finally out of the ancient and the medieval world. But here's the thing. You cannot separate the early modern thing that we call the scientific revolution from this whole long story. Because it's not just the story about the vexing problem of retrograde motion, although that's the key, or at least one of them. But it's, how do we know what we know? How do we learn new things? How do we push the boundaries on our sense experience? How do we move forward with knowledge? All these pieces are a part of that broader mosaic, that bigger puzzle. You can't take any of them out. You can't leave any of those out, because it is a story that is built over time through these questions and through failure and success. Roger Bacon was an alchemist, for heaven's sakes, right? He was trying to transmute lead into gold. So he's not perfect by any stretch of the imagination. But he thought there had to be a systematic and methodological way, instead of just fooling around, doing things haphazardly or randomly. And what's interesting is that through his alchemy, he became a better chemist long before we even knew what that word meant, because of the things that he explored and the way that he challenged himself and the authorities around them. How do you verify things? How do you prove them? How do you move forward? And so we jump forward now to this guy. And now this is an image you may actually find familiar. This is Nicholas Copernicus. And we're finally going to wrap ourselves back around to the story of what we had been talking about, back when we were talking about Aristarchus, all those minutes ago, right? Because Nicholas Copernicus, a Polish priest, right, and scholar, and there's the thing, those two things always seem to go hand in hand, because who were the people who were educated? Oh, that's right. At least in the Christian West, the priests. That's where most of our scholars are coming with. Copernicus, Roger Bacon, right? There are others, right? And especially at this time, because he's born 1472, dies in 1543. So right smack in the middle of what we call, oh, that's right, the Renaissance and the Reformation. And so here comes Nicholas Copernicus, Catholic priest, budding scientist. He will first study at the University of Krakow in Poland. He will also study canon law at the University of Bologna in Italy. The University of Bologna is where he first is introduced to humanism. By that point, pretty much every university had a few humanist scholars on their faculties. And in that desire to dig deep into sources, to question everything, to poke and to prod, young Nicholas Copernicus is introduced into a much broader world. And he had that kind of mind. He will go on to study medicine at the University of Padua, right? And a part of the typical standard course of medicine, right, was studying astrology. Yeah, astrology. How the stars and the planets and the celestial bodies have an influence on our lives. We still have astrologers running around, right? But the interesting bank shot of studying astrology back then is that you got a good dose of astronomy along with it. That's something our astrologers don't do particularly well. That's because after we actually move out of the Middle Ages, pretty much everybody recognizes that astrology is bunk. The stars, I hate to say it, do not control your life or your moods or anything else. They don't care because they're just giant balls of gas. They're not sentient. Doesn't have any impact on you. Because frankly, the light we see and the movements of them happened so long ago that they're probably gone. Right? Like the farthest distance away we can peer is like 13 billion light years away. Well, that's 13 billion years ago. So no, they don't have any effect on your daily life. Just thought I'd point that out. But there's Nicholas Copernicus studying medicine, and a part of it is astrology. And because of that, he's going to learn some astronomy. And all of this starts swirling around in his head. And when he goes back to Frombork, which is a coastal town in northern Poland, to serve as a canon, essentially the bishop's assistant, because that's what his job was, which gave him a very comfortable life. He served as a canon at the cathedral, right, this bishop's assistant. And around the year 1510, so just pretty much same time as Luther is getting going, he starts studying astronomy. He moves beyond astrology, and he just starts studying the sky, charting the course of the stars and the planets and all of the rest. And he comes back to something just baffles him, frustrates him to no end. And that is, well, let me put it back up. Ptolemy's equant. Copernicus looks at that and goes, oh, that just doesn't work. It makes no sense. It makes no sense. And so between 1510 and 1515, he starts writing an essay introducing a wild notion called heliocentrism. The sun is at the center. What he introduces is Aristarchus's model. There's this Polish priest and scientist and astronomer, and this is what he comes up with, without knowing Aristarchus's discoveries or his writings. But the more he calculates the way things work in the nighttime sky, the more this is the only thing that makes sense. It's the only thing that truly describes and explains what's actually going on out there. And he begins to write his masterwork on the revolutions of the holy and the heavenly spheres, on the revolutions of the heavenly spheres. He works on it his whole life. And he actually held a published copy of it in his hands on May 24th, 1543, the day he died. On his deathbed, he was able to see his life's work was published. It's an amazing piece because it describes mathematically and through observation a heliocentric model of the universe. The preface of this, when it was published for mass consumption, which at this point was like 500 or so copies, was written by a Lutheran scholar named Andreas Osiander. And Osiander hedged a lot because he remarked that the theory was merely a mathematical model and not physical truth. And that's essentially what kept Copernicus's name from being dragged through the mud as a heretic. People disagreed with the Copernican model. Couldn't possibly be that. Couldn't be. He couldn't be right. It changes everything. And now think about what's going on at the time of Copernicus, when he publishes on the revolutions of the heavenly spheres. The Reformation is in full swing and has splintered Christianity. The explorers from Europe have been gallivanting around the world. By this point, there's not a place on the map where European explorers haven't been and started their conquest. They've claimed everything, even in what they called the New World. By the 1540s, the Spanish have conquered the Aztecs, the Incas, and the Mayas, all defeated. The world that they understood had changed so dramatically, so radically. The Reformation and the conquest of the world, all of a sudden there were additional continents to deal with. The world, as they understood it, was radically being reshaped. And that was enough. That was so big for so many people that it was almost too much. And it freaked them out. And then comes Copernicus saying, you know, that whole model of the universe that you got? Yeah, it's wrong. It's wrong. Aristotle was wrong. The church was wrong. Everybody. Whole thing. It's got to go. No wonder they were like, oh, no. That's lovely. It's just a mathematical model. right? Just a mathematical model. That's not physical truth. It's a lovely theory. Of course, the thing about theories is that they're true until you prove them false. Some are easier to prove false than others. This one, that's a sticky wicket, and no doubt about it. But of course, Copernicus wasn't around anymore to have to worry about it. And that was the interesting bit, right? There he is. And there he isn't. But his ideas stick. Because they explain so much. It makes so much more sense. But it's not the end of the story either, is it? It doesn't fully explain everything. But boy, it gets us a lot farther along. And you can see that this opens the door for scientific inquiry into everything. Humanism really gives it a boost. But they've been building on this for quite some time because they're trying to figure out how to make sense of the world in which they lived and our place in it. And they're going to say continually on, we got to keep pushing. And so they do. The scholars keep coming, right? And now the names, these start to become so familiar to us. Tycho Brahe, best facial hair in all of the early modern period. No doubt about it. I couldn't grow that if you paid me. And I wouldn't want to, frankly, because it's ridiculous. But he wore it well. Tycho Brahe, 1546 to 1601, right? Little farther down, he's going to revolutionize astronomical instrumentation. He's going to profoundly change astronomical observation. His star charts, right, and his data is going to be some of the most prized possessions of any navigator in the world. He studied stars and comets and articulated their position well beyond the moon. He challenged the Aristotelian model of the universe, but he did not embrace the Copernican model. He posited a bit of a hybrid, a geocentric universe, we're still in the center. The moon and the sun orbited around the Earth, but with a heliocentric explanation for the rest of the planets. So they all orbited around the sun, but the sun and the moon orbited around the Earth. I don't have a lovely drawing for that because that one just, it hurts my head. It does explain retrograde motion, but unfortunately, it breaks every law of physics to do it. But he was a compiler of data. And that data was going to be used by others to say, oh, wait a minute. He's got good raw material, but his conclusions are all wrong. And that's okay, because he kept fine-tuning the instruments and kept working on the observation, and he took meticulous records. You need people like that. You need the people who just live for the details, for the data. And he did. Make no mistake about it. And he's going to keep pushing. And he's going to open doors for others to walk through, as all of these others have done. They keep pushing the boundaries. And one of these times you're going to get people that walk through like this. Galileo Galilei, 1564 to 1642. Galileo is one of those people that we talk about as being one of the central figures in this whole grand story about the scientific revolution, because what he is going to do is he's going to give us some physical components. So much of this can be reduced to abstractions, mathematics, geometry, and all of the rest. Galileo is going to improve some very basic things. One of the first things that he's going to improve is a telescope. Telescope was often used mainly for naval uses or the military. We looked at each other or kept it on this plane, right? He said, why don't you point that telescope up? Let's look up with this device. And he improves its magnification. And when he looked through it, when he experienced those first visions, it changed everything. I mean, he took a common device, improved it a little bit, and said, let's look up. And he looked at the moon. And you know what he saw? Not something that was even or ephemeral. Not just a light or smooth surface. He saw pockmarks. It was uneven. There were ridges, valleys, mountains even. That's what we look at. When we look through the telescope, we see the moon for what it is, a surface that looks a lot like Earth, and it's very tangible when you look at it, right? You can see its substance. And when Galileo looked at the moon through his telescope, it changes everything. Because now it's not just an abstraction. And you know through magnification that it's a long way away. You can do that mathematics. It's not that hard. And so now he's really pushing the boundaries, and this is what really scares them. And of course, the other thing that really annoyed the church, especially, is because Galileo knew them very well. I mean, the people that he fought with were the cardinals and the bishops and the popes that he knew particularly well. And Galileo, not unlike, well, Socrates, was not the most humble of people. Galileo lived to tweak the authorities or people who disagreed with him, right? He was not awesome as a human being. He had an ego. And so the fights with the church made sense because in many ways they were fights about the status quo and they were fights about personality. But he kept going and he kept saying, look at this, look what I found. Not just the moon, the Milky Way, that broad white stripe in the sky that we can't usually see down here in the Detroit area because, or in any metro area because there's too much light pollution. That thing, yeah. They thought it was just a big stripe. And he says, you know what? It's actually made up of countless other stars. Can you imagine? I mean, because you can count the number of stars in the nighttime sky. You can catalog all of them. And then there's the Milky Way. And you figure, oh, it's just a big white stripe out there, right? It's so much more than that. It's a galaxy worth. And all of a sudden the universe keeps getting bigger and bigger and bigger. And folks like Galileo say, that's okay, it makes sense. It makes perfect sense. He looked at Jupiter, that giant planet, and then realized, oh, look at that. Jupiter has moons that orbit around it. Each discovery led him closer to Copernicus's theory. And finally, he did the thing that got him in the most trouble. It's not simply a mathematical theory, he argued. It's not. It's scientific fact. It is as solid as this table, this theory of mine. It's provable. I can show you with the math and with personal observation And that's what drew him into the conflict. Because now he was challenging the status quo, the Aristotelian worldview that the church had adopted, lock, stock, and barrel. I mean, dissing Aristotle was huge. That bothered people to no end because in many ways, the Catholic Church was built on the model of Aristotelian thought. It explained everything, the universe, sacraments, you name it. And he was saying, yeah, not right. It's not right. And essentially saying that the system that everybody had used all these years, it's flawed. Because it was. And in the midst of this huge fight with the church, he said, and this is one of my favorite quotes of all time, I do not feel obliged to believe that the same God who has endowed us with sense, reason, and intellect has intended us to forego their use. Right? Galileo was not an unbeliever. He was still a faithful, dutiful son of the church, to use the old archaic language. But he didn't think that God should be limited or closed into a box. And neither should we. I do not feel obliged to believe that the same God who has endowed us with sense, reason, and intellect has intended us to forego their use. And his fight with the church shattered the old norms and the status quo. Here was somebody willing to throw it all up into the wind, to prove a point, and to get the immovable object to move. Not the church, the status quo. Power. The church just happened to be the people who had it at the moment. But make no mistake, any power will always resist the change in the status quo because it threatens them and it threatens their authority. And that's what bothered the people about Galileo. He challenged them and their system. And he had the evidence, the receipts, as it were, to back up his claims. And an ego to continue to drive it forward. The fight between Galileo and the church is what we remember. But even Galileo understood that he was standing on the shoulders of giants, as Isaac Newton will actually say down the road. As they all knew, they knew they were building on a system. They were building on the work of all of these generations past. They were pushing the ball forward in their time, but they knew that the ball had been moved. Change scares people, and never more so than when it seems to threaten their livelihood. But Galileo knew and believed how important it was to continue to move this forward. Which finally opens the door to the last couple of folks that I want to talk about today, because the next one is an unassuming guy. This is Johannes Kepler, 1571 to 1630. He was a student of Tycho Brahe. And whereas the other astronomers still followed the ancient precept that the study of planets is a problem only in kinematics, kinematics is a branch of mechanics concerned about the motion of objects without referencing the forces which cause the motion, right? Things move. We don't care how they move. They just move. Kepler's like, that doesn't work. Kepler is going to say, the only way this makes sense is if we actually introduce physics into our study of the heavens. How do things move? Right? Why do they move? In what way do they move? What forces are involved? Kepler introduces physics into astronomy. And we're like, it took that? Yeah. Because the whole notion of physics was still developing at the time. I mean, it's not even fully realized, right? We're not to Newton yet. And there's Kepler. He supports Galileo's astronomical observations. And then Kepler solves the big problem of retrograde motion. Firmly, convincingly. He takes Copernicus's model, Aristarchus's model. He says, I've got 2 more tweaks to that. Because you see, there's a problem. And I'm going to go back to Aristarchus. This is the model that Aristarchus used, obviously, but also Copernicus. Notice a problem? There are 2 problems. One is that all of these orbits are concentric circles, right? And not only are they concentric circles, perfect circles all the way out, because that's the easiest way to describe it, they're also 2-dimensional. It's on a plane, essentially. And Kepler's going to say, yeah, that's not the way it works. Because it's not everything is, in concentric circles along a plane like this, right? That's not the way it is. He introduces the concept of elliptical orbits. So you may have the sun right here, and then Mercury, and then Venus, right? Even the Earth, right? And some of them, the farther out you go, the more irregular or elliptical actually they are. And so you get ellipses, ovals, and beyond, not circles. So that's one of it. The other one, so elliptical orbits, that helps to explain things. But the other is irregular, meaning we keep thinking in 2 dimensions when we think about all the planets, right? They're all on this plane, and all the orbits are going to work along that. Well, Kepler is going to introduce the other axis. Some orbits are going to be on this plane. Some are going to be tilted, right? Because space is 3-dimensional, and not every orbit is going to be on the exact same plane. And so between elliptical orbits and irregular orbits, and the fact that they're all going around the sun and not the Earth, so heliocentric, not geocentric, that explains the question of retrograde motion. But we're not done, because there's still one more problem. See, it's not just retrograde motion. It goes back to Aristarchus, who said, no, see, we rotate on an axis and we orbit around the sun. And that's the whole business about why can't we feel it? And that's where this nice guy comes into this. Isaac Newton, 1643 to 1727. One of his most important works, the most perhaps in all of this history of science, was written in 1687. It was called the Principia, the mathematical principles, essentially, of everything. And in this, he's going to describe the laws of motion, how things move, right? First law, an object will not change its motion unless a force acts on it. We know these, right? We could probably recite them. The second law, the force on an object is equal to its mass times its acceleration. The third law, when two objects interact, they apply forces to each other of equal magnitude and opposite direction. Well, that starts to answer, or at least inquire and move forward, Johannes Kepler's questions about physics, right? It's not just kinematics. It's not just mechanics that, are concerned with the motion of objects without reference to the forces which cause the motion. He's going to explain this. And it's all going to wrap her up with this wonderful thing called the concept of universal gravitation. Right? I'm going to read this one specifically. Any particle of matter in the universe attracts any other with a force varying directly as the product of the masses and inversely as the square of the distance between them. He's got the mathematics. He'll invent calculus to help explain all of this. So when you're having your fun with calculus, just remember Newton. But he shows how it all works. The mechanisms, the forces, the mathematics, and it's all there. Now, we've moved beyond Newton's classical physics, right? We can thank all of our scholars in the 20th century for introducing a next step. But up to that point, it explains what's going on, including why it is that we don't feel the speed of our rotation and our orbit. It's gravity. It's why when we jump, we don't just, the earth doesn't spin under us. All of these things explain the way we live and how we interact with the natural world around us. And every step along the way, they kept pushing those boundaries out. And they developed methodologies to allow us to take the necessary step-by-step process of learning how this all works. And in the process, folks like Isaac Newton are going to come up with a mechanistic view of the universe, that it's a machine that works like clockworks. It makes sense. And so whereas in the beginning of all of this story, the universe seemed very small and kind of mysterious and unknowable, the farther we push forward, the bigger the universe gets, the more it makes sense. Through a scientific and mathematical exploration of how everything works. Once we've done that, once we've seen the benefit of scientific inquiry and exploration and experimentation, then it just sprints forward. And there isn't really anybody holding them back. There is no authority strong enough to contain this intellectual explosion. Even the church couldn't stop Galileo. And afterwards, they kind of stopped trying. Oh, they threw their fits all the way up into the 19th and even in the 20th century. We still have people today who panic every time science takes another step forward, but they can't stop it. because there's just not that amount of control. Even in the church, even in the early modern period. It's an interesting thing because at the same time that the scientific revolution is going on, the church and society are trying to get rid of witches. And that really is a story for another day, but it's the same story. People who are in power, wanting to maintain power at all costs. And in both the scientific revolution and the witch trials, what they're going to discover is they can't. Because ideas are powerful. And our questions are powerful. And our inquisitiveness, our curiosity will continue to drive us forward. In strong state-controlled regimes, there's always, it makes sense that they go after the intellectuals and the artists first. Because those are the dangerous people. Those are the people who pose the greatest threat to those who maintain the status quo. And so the vexing question of retrograde motion is really a question of saying, okay, you say that's how the universe works, but that doesn't make any sense. Let's find out if we can get closer to the truth. That's where we are. And that's the climate that we see all during this period. Pushing, inquiring, challenging. There's a reason why we study this time period, and this may be one of the biggest. Because this is who we are. As civilizations and as individuals and as students, that's who you are. You're supposed to be challenging the status quo. You're supposed to be pushing to make the world a better place and to make it more knowable and understandable. That's your job. Our job as teachers is simply to give you a story and some tools and then let you go. I look forward to seeing where you go next. Thanks, everybody. And I look forward to our next lecture in which we will dive right in to the English Civil War. Thanks so much, everybody. See you next time.